For the last part of our notes on light waves. To start off, we're just talking about generally what the different types of light waves, their general features. Okay, they'll have, we can characterize them in a number of ways. We can compare things like their frequency, their wavelength, stuff like that. But we're just generally kind of comparing and seeing what each type is used for. Okay, all electromagnetic waves, including visible light, move through empty space at what speed? Very good. I know you all said it at home. 3 times 10 to the 8th meters per second. There's a reason I'm emphasizing that so much, guys. It's very, very important. Different types of electromagnetic waves. They all have the same speed. Okay. You can also call them, technically they're radiation. Okay. We tend to think of radiation as bad. Radiation just means waves. Okay. Energy in the form of waves. They all have the same speed, but they all have different frequencies. They all have different periods. They all have different wavelengths. They all have different amounts of energy. Okay, so what we're going to be doing today, or in this video, is looking at the different types and kind of generally figuring out their characteristics. You need to have your reference tables, or at least the picture on the front with all the different types of waves in front of you now, because I'm going to be referring to that a lot. Now, as you're looking at that picture, one of the questions you might have is, how come there's some overlap? Okay, so for instance, from the wavelength of 10 to the negative 9 to 10 to the little bit before negative, about halfway between negative 10 to negative 8 to 10 to negative 7, it looks like X-rays and ultraviolet overlap. And that's true, they do overlap. Okay, that's okay. I just need you to add this in somewhere. The ranges on this picture can overlap. The reason that they overlap, that it's not just one and then it turns into the next, is because these are classified, these types of waves, they are classified based on how they are generated. Okay, how they're created. That's how they're classified. So that's what makes, let's say, an ultraviolet radiation different from X-ray radiation, even if they have the same wavelength and frequency. One was created one way, one is created another way. All right. Now, what we're going to do is we're going to start at radio waves and move up towards gamma waves. And when I say up, I'm really talking about up in a couple of categories. We're going to start off with waves that have long wavelengths and low frequencies. Now, if the frequency is low, frequency and period are inverses. If the frequency is low, that means the period is very high, or you could say long. Okay? So long wavelength means low frequency, which means long period, and it turns out that this also means radio waves carry very low amounts of energy. And we're going to move, as we move down, you'll see how these change. Again, please have that picture out in front of you. We're going to start with radio waves. Okay? The frequency of radio waves. Anything less than 10 to the 10th hertz are in the frequency range for radio waves. Okay? The wavelength range is anything greater than approximately 10 to the negative 2 meters. Now, 10 to the negative 2, that's 0.01 meters. That's a centimeter, okay? My pinky is a centimeter big. Anything with a wavelength bigger than this is considered a radio wave, okay? This includes, as I alluded to last time, this includes radio waves on the picture, it includes television waves, it includes, and I don't really understand why there's a distinction here, your FM and your AM dials on your radios, okay? Those are all types of radio waves. And the way that you get radio waves, and the reason you have car antennas, is that they are produced and received by charges accelerating in a wire. The reason you have a car antenna is because that thing is made out of metal, right? Well, if it's receiving radio waves, the radio waves will cause the electrons in that car antenna to bounce up and down, to move up and down through that. And based on how they are moving, your radio can figure out what sounds it is supposed to play. I don't pretend to be an expert in exactly how that works, but essentially your radio will read the patterns that are coming in off that antenna, how the electrons are moving, what types of radiation it's receiving, and it will convert that into sound that comes out through your speakers. All right? So it's produced, and this is how you produce radio waves, this is also how you detect them. Most important thing, please do not think radio waves are sound waves. First of all, EM waves, we draw them like this. That's a longitudinal wave, okay? That is purely longitudinal. Oh my gosh. That is transverse. Sound waves are longitudinal. Okay, sound waves are pressure waves. That is completely different. So sound waves are longitudinal. Radio waves are, on the other hand, transverse electromagnetic waves. EM is the abbreviation for electromagnetic, okay? They are not sound waves. We take radio waves, and based on what the properties of that radio wave are, we can convert that signal into a sound wave, but they are not the same thing. Please do never ever tell me that a radio wave is a sound wave. I'll freak out. If you want to see me freak out, do that. Some of you probably want to see that. Microwaves, okay? Next up, please be looking at those pictures. The range for microwaves for frequency, anywhere from 10 to the 8th up to 10 to the 13th hertz. Again, hertz being the units of frequency. And a wavelength range of 10 to the -6th up to 10 to the -2nd meters. 10 to the -6 is like a millionth of a meter. So this is pretty small, and it's still like the second longest wavelength. We use microwaves to communicate. Okay? They're used in communication systems, in air or in space. And we also use them to cook food. That's why we have microwaves, okay? Here's what happens. The molecules in the food, remember we talked about natural frequencies a little bit ago. The molecules in the food have natural frequencies that are similar, or basically the same in some cases, to the frequencies produced by a microwave. So, you turn on a microwave, it produces microwaves, the radiation. That radiation hits the food, it causes the food molecules to start jiggling, okay? They resonate, they move back and forth, they vibrate. And when things move back and forth, if they're moving back and forth next to other molecules, they're going to give off some of that energy in the form of heat. So you get all these molecules kind of bouncing around, jiggling around, vibrating inside, and that's producing heat. Cause your food to warm up. Here's our first two. We're going to talk about infrared rays next. Okay, that's the next topic on your. That's the next the next category down or over on the picture. We're moving from right to left, if I remember correctly. Infrared waves. I always thought that when I was younger, for some reason, I just couldn't get infrared into my head. I just always read this as infrared for some reason. The frequency range for infrared waves goes from 10 to the 11th up to 3 times 10 to the 14th hertz. Wavelength range, I screwed up the wavelength range for microwaves. I apologize. Sorry, you can go change this. Some of you probably already noticed this. For microwaves, the wavelength range is supposed to be 10 to the -4th to 10 to the 0 meters. Okay, that's for microwaves. Please make that change. I must have been looking at the wrong one. Infrared is still from, so microwave frequency range is 10 to the 8th to 10 to the 13th. Infrared is definitely 10 to the 11th to 3 times 10 to the 14th. But the wavelength range for infrared waves is not this. It is 10 to the 6th to 10 to the -6th, all the way to 10 to the -2nd meters. I apologize for that, guys. That's a frequency range for infrared waves. This is radiation that's given off by warm objects. Okay? Objects that are hot or warm in general, they give off radiation, in the form of waves. And it turns out that the frequency that they give off puts them in the infrared spectrum. Because of this, infrared waves are used to heat things. Your space heater gives off infrared waves. They're also used in things like night vision goggles or heat-seeking goggles, okay? At night you can't see because there's not a lot of visible light. However, objects don't stop emitting energy just because it's nighttime. They're still warm, they still give off that radiation. Night vision goggles essentially look for infrared rays, and then they just kind of translate those rays into something we can see. That's why it looks all green. I wish I had a pair that I could show you guys here. so they turn into night vision goggles. Okay, or that is how night vision goggles work. They search essentially for infrared waves, and then they convert that into something we can see. All right, that's what infrared waves are used for. Heating, night vision goggles, heat-seeking goggles, whatever you want to call them. Visible light. Okay, the visible light range goes from approximately 3 times 10 to the 14th hertz up to 8 times 10 to the 14th hertz. Again, please notice how small a range that really is. The wavelength range is from 3.75 times 10 to the negative 6th to 1 times 10 to the negative 6th meters. Tiny, tiny range. Okay. Probably at some point you might have learned about how vision works. There are special cells in your eyes, rods and cones, and they intercept this type of light. This light goes into your eyes, and it registers on those rods and cones. It interacts with it, and those signals go to our brain and convert it into something that we can interpret as what we are seeing. Okay, I'm not going to talk any more about visible light really right now. That's essentially what's happening. Special cells or rods and cones in your eyes. Next one, ultraviolet light. Frequency range of 8 times 10 to the 14th up to 10 to the 18th hertz. Okay, the wavelength range goes from 10 to the negative 9th up to 3.75 times 10 to the negative. I'm just writing everything wrong today. This is not good. 10 to the negative 7. Please make that change. Not that it really matters that much, but I can't say when I write things down wrong. Ultraviolet light, you guys know this. You might hear of UV rays or UV radiation or UV light. This is the type of radiation that causes sunburns. Now, how do you protect from that? Put on sunscreen, number one. But there are actually a lot more UV rays than reach us down here on Earth. A lot of them get filtered out by what we call the ozone layer. Okay? It helps protect the Earth from UV rays. This is why we want to keep the ozone layer. Because if not, there would be a lot more harmful UV rays reaching us, and possibly some other stuff too, that we don't want around that would cause very, very bad things to happen. Not just like the incidence of skin cancer would go through the roof if we were getting more rays, UV rays. It would be very bad, and it would be bad for other reasons too. Okay? There's a lot of reasons why we want to keep the ozone layer around. We don't want to destroy it. Second highest type of radiation on our chart are X-rays. Frequency range for X-rays goes from 10 to the 16th up to 10 to the 20th hertz. The wavelength range is from 10 to the negative 12th up to 10 to the negative 7th meters. Okay? These are very powerful rays. They are used by doctors to image body parts. But it turns out they're also very high energy, and they can be dangerous. There's a reason the doctors put that big lead apron on you when you take an X-ray. Okay, when you go to the doctors, if you break a bone, they put the lead on you. If you go to the dentist, they still do if you go to the dentist. You don't need that type of radiation going through your body unless it's absolutely necessary. So as a precaution, they put a lead apron on you. Lead tends to stop X-rays. So what they do is they're protecting your body from needless exposure to X-rays. Okay, just the parts that need to be imaged. But the key thing is they're very high energy. And one of the things that you should know is that as you go from radio waves down, one of the things that happens is they become higher and higher energy. They become more and more energetic. And I'll write that in just a second as soon as I'm done erasing this. The last type of radiation that we're going to speak about is our gamma rays. Gamma rays are truly, truly kind of weird. You only get them in a certain number of cases, okay? Very specific situations. So, the frequency range on gamma rays is anything greater, or is not anything, but can be greater than 10 to the 18th hertz. The wavelength range is typically smaller than 10 to the negative 10 meters. Now, this doesn't mean that X-rays are gamma rays. They're two different types of radiation because they're produced differently. The two places you need to know about that gamma rays come from, and this used to be in the physics curriculum, and it will be in a couple of years. They're going to bring this back. But radioactive decay releases gamma rays sometimes when you have elements changing into other elements. That releases gamma rays. And also, gamma rays come from deep space. Certain events that happen in space cause gamma rays to be emitted. And those are the two places gamma rays come from. They are extremely dangerous. You do not want to be in the path of a gamma ray. Very, very high energy. Okay? Very high energy. As you can see, they have a very small wavelength, a very short wavelength. They're extremely high frequency. They also must have, if they're high frequency, they must have a short period. So you can see how these are all related. The big thing I want you to remember, because this will be important in about a week or so, is that high frequency means high energy for light waves. Up there, with radio waves, we have low frequency and low energy. So as the frequency increases, the energy increases as well. That's a crash course in the electromagnetic spectrum. You need to become familiar with that chart. And we are almost done with the waves topic.